Thanks for the introduction, Randy. I'm Brian Connelly. I'm the Development and Operations Hydrologist at the North Central River Forecast Center. We're up in Chanhassen, Minnesota. And I'm going to talk to you today about the Hydrologic Ensemble Forecast System. It's a system that we use to quantify the uncertainties associated with hydrologic forecasts for timescales of hours to even years into the future. The HEFS is being implemented at all National Weather Service RFCs, and coverage will expand gradually over the coming months and years. There will be ample opportunity for feedback from partners and users as the implementation progresses. And the purpose of this talk is to give you an overview of how HEFS works and to provide some examples of it. Craig Schmidt will provide examples after I'm done. I believe we're going to kind of wait until both Craig and I are done before we field any questions. If people do have questions, Randy, should they just put them into the GoToWebinar chat or?
Yeah, they can either raise their hand or they can type them in the questions pane of the GoToWebinar. And then I will go ahead and either unmute them if they raise their hand or ask their questions at the end.
Great, thank you. Okay, so here's just the agenda for today's talk. We're going to talk about ensemble forecasts. What are they? Why use them? And then we'll talk a little bit more about HEFS, what the goals of the product are, how it's structured, what goes into it, what comes out of it, and how things are processed. I'll talk a little bit about status of implementation and applications for our service area in particular, and then we'll move on to a little bit of a case study by Craig Schmidt. So what are ensemble forecasts? Before I talk about that, I just want to say that kind of the single valued forecasts have been the foundation of our hydrologic forecasting since the RFCs began. So single valued forecasts like the ones shown on the HEFS pages, they're invaluable to our users. They're a culmination of a forecast process overseen by experienced forecasters using a variety of resources, including hydrologic and hydraulic models, core partners, such as the U.S. Army Corps of Engineers and the U.S. Geological Survey, local WFOs, and local officials. We also use historical analog events and much more goes into that process. Those forecasts, the single valued forecast on HEFS pages, have been referred to as a gold standard nationally and across the globe. However, those forecast hydrographs on HEFS include only 1 or 2 days of QPF. And our users need to know what may happen to the rivers from weather events further into the future. As uncertainty increases with lead time, our users also need to see that reflected in our forecasts. Ensemble forecasts, like the HEFS, explicitly quantify the data and modeling uncertainties. Each ensemble member represents one possible outcome, and collectively, all the ensemble members aim to capture the range of possible outcomes. The calls for ensemble forecasting originate from scientists, operational forecasters, and decision makers alike. In weather and climate forecasting, ensemble techniques have become standard practice for quantifying uncertainty. Increasingly, these techniques are also becoming standard practice in hydrology. For operational forecasting, the methods used to assess and communicate uncertainty must be objective, practical, and simple to implement, and simple to understand for the average user. While end users vary in their needs and levels of sophistication, they are interested in better understanding the risks associated with too much or too little water. An understanding of the different possible outcomes and their probabilities is critical to managing risk, because some of those outcomes involve large costs, whether the cost of doing something or the cost of doing nothing. Ensemble forecasting has become standard practice in meteorology, and there are many operational weather and climate models that use ensemble techniques. Examples include the North American Ensemble Forecast System, or NAEFS, and the Global Ensemble Forecast System, GEFS, which is part of NAEFS, and the Short Range Ensemble Forecast System, the SREF. In order to leverage these ensemble forecasts and to translate their skill into hydrologic forecasting, there is a need for hydrologic modeling tools that can process ensemble weather and climate forecasts. However, weather and climate models produce outputs at different temporal and spatial scales than hydrologic models, and frequently contain biases in precipitation and temperature. Therefore, it is generally not advisable to use the outputs from the weather and climate models directly in hydrologic models. Rather, it is necessary to bias correct and downscale these outputs for use in hydrologic modeling. The HEFS provides tools to accomplish this. Ultimately, the goal of ensemble forecasting is to support better decisions about water resources by end users. A single valued forecast does not explicitly provide information about the range of possible outcomes and their probabilities. Therefore, the interpretation of a single valued forecast involves a large degree of subjectivity. In contrast, an ensemble forecast provides an explicit assessment of the probability that a particular river stage might occur. In this sample graphic here, we can see from the different probability levels that there's a 10% chance of a moderate flood and a 25% chance of a minor flood produced by the HEFS process. You know, that's a lot more than a single valued forecast can provide, a lot more information. In order to capture the skill in ensemble weather and climate forecasts as a basis for more informed water decisions, the NWS has developed the Hydrologic Ensemble Forecast System. NWS has traditionally used ensemble streamflow prediction, ESP, shown in the second column of this table here, to produce ensemble forecasts of streamflow for the long range, you know, going out 2 to 3 months. However, this system has several limitations and needed to be improved. In particular, ESP uses climatological forcings, which is only appropriate for seasonal or long-range prediction. It is not suitable for short to medium-range forecasting, like 1 to 2 weeks, as weather forecasts improve substantially over climatology or historical observations at these timescales. The HEFS accommodates weather and climate forecasts from a variety of sources, including the RFC quantitative precipitation forecasts and quantitative temperature forecasts, as well as ensemble weather forecasts from the GEFS and the CFS. In addition to using weather and climate forecasts, the HEFS has the ability to capture the uncertainty in the hydrologic predictions and corrects for biases in the forecast probabilities, which is something ESP is not able to do. As such, the forecast probabilities from the HEFS should be more accurate and more skillful than ESP. especially with future development and enhancements. The HEFS also has a capability to provide a more comprehensive suite of forecast products for end users, including products for the short, medium, and long range, and verification products that will allow users to objectively assess the strengths and weaknesses of the HEFS forecast for their applications. So, ultimately, the aim of any hydrologic ensemble forecasting system is to quantify the total uncertainty in the hydrologic forecasts. And this is the aim of the HEFS. Unless the total uncertainty is quantified adequately, the forecast probabilities cannot be accurate. In other words, the ensemble spread will not consistently capture the observed stream flow. The total uncertainty originates from two main sources. One is the weather forecasting, or forcing uncertainty. That is the uncertainty about the future values of temperature, precipitation, and any other forcing variables used by the models. And two, the hydrologic uncertainty. The hydrologic uncertainty comprises all of the uncertainties associated with hydrologic modeling, including the initial conditions, model parameters, model structure, and any other operations such as manual modifications to the hydrologic model states and modeling of river regulations at reservoirs. The HEFS aims to quantify the total uncertainty in order to produce accurate forecast probabilities. As such, the HEFS includes separate components for modeling the weather forecasting uncertainties and the hydrologic modeling uncertainties. In this chart, there's kind of an example of how the uncertainties are captured. The weather uncertainties captured in the green area, and the blue areas are the hydrologic uncertainty. This is just kind of a graphic to give you a visual idea of how that is done. So, how does this process work in practice? This slide shows the main components of the HEFS and how they account for the two sources of uncertainty that we talked about in the previous slide, namely the weather forecasting uncertainties and the hydrologic modeling uncertainties. The forcing uncertainties are represented by the green boxes, and the hydrologic uncertainties are represented by the blue boxes. The Meteorological Ensemble Forecast Processor, MEFP, shown in this green box here, captures the forcing uncertainties and corrects for biases in the forcing inputs to the HEFS. Specifically, the MEFP ingests raw forcing information from multiple weather and climate models. The MEFP corrects for biases in the forcing inputs and downscales them for input into the hydrologic models. Okay, we're going to start by talking in a little bit more detail about the MEFP, or the Meteorological Ensemble Forecast Processor. I want to be really clear about this next point. I mentioned this earlier, but I think it bears repeating. The HEFS does not use the raw precipitation and temperature time series or temperature ensembles generated by the MET models. The raw ensembles may be biased compared to the time series that we use to calibrate our hydrologic models. If we use the raw ensembles, these biases would transfer to a bias in the hydrologic ensemble. Therefore, the MEFP was developed to create unbiased temperature and precipitation ensembles. The MEFP quantifies the uncertainties in the raw weather forecasts from the weather and climate models and corrects for biases in these forcing inputs. The MEFP produces bias-corrected ensemble forecasts of mean areal temperature and mean areal precip at the subbasin scale. The MEFP can ingest raw forcings from RFC deterministic forecasts as well as ensemble forecasts from NCERF's weather and climate models. For ensemble inputs, the MEFP uses the ensemble mean forecast only. So although models like the GEFS are producing an ensemble of possible weather outputs, weather forecasts, HEFS is only going to utilize the mean of all those ensemble members to come up with an ensemble to drive the hydrologic models. So, and we'll see how that works in the next slide here. So, in order to generate the unbiased precipitation and temperature ensembles on an operational basis, we need to compare meteorological hindcasts with our historical calibration forcings. The left plot in this slide shows a joint distribution of forecast values along the x-axis and observed values along the y-axis. This could be a chart for either temperature or precipitation. The joint distribution is generated from a data set of ensemble means from the hindcasts versus the actual observed values that occurred. So, operationally for a given ensemble mean forecast value, the MEFP takes a slice across this distribution at the forecast value, which in this case denoted here by the Z subscript FCST line. So from that, it can get a conditional distribution, which is the probability of the possible observed values. And that's based on an analysis of the historical observed values and the hindcasts. And so what the MEFP can do is it looks on the probability scale here, and it kind of takes a stratified sample of the probability axis, comes across to the distribution, and comes up with a possible observed value. It does that for each of these probability levels. And that's how it can come up with an ensemble of possible precipitation or temperature values for a given day for a given subbasin. So after going through that process for precipitation and temperature, we now have an ensemble of values for each day for each subbasin. This map shows all of the subbasins that we have in our service area. I think there's over 1,400 of them now. And so for each of those subbasins, for each day of the forecast period, we have an ensemble of possible precipitation and temperature time series, or values, excuse me. So the next goal is how do we take those ensemble values for each basin for each day and piece them together into a time series that is realistic. Do we take the highest value for each subbasin and put that into an ensemble, and the lowest value and put it in an ensemble? That's probably not likely, a likely thing that's going to happen. So, in other words, how do we preserve the space-time coherence? We know that meteorological events are correlated in space and time. Temperatures tend to be correlated from basin to basin and from one day to the next, as well as during the day. We know that large-scale storms can be more persistent in space and time than rain showers. And there are also relationships between meteorological variables. So that's the question is, how do we take these ensembles for each subbasin for each day and piece them into a reasonable time series to force the modeling? The example, or the process, was developed by John Shocky. He was a hydrologic scientist for the Weather Service. And the process is called the Shocky Shuffle. So the scheme is the members of the ensemble are arranged in such a way that the ordering of the members matches the ordering of the corresponding historical observed values in magnitude and associated years. And I'll show an example of this in a moment. The effect is that the ensemble members are ordered according to the historical realization of the observed. Using this approach, the observed intersite correlations, intervariable correlations, and the observed temporal persistence are almost entirely recovered. So here's a kind of a simple example. Let's say our HEFS product is based on an ensemble of 5 members. And those members are based on the observed meteorological forcings from the years 2015 to 2019. In the second row of the table are the rankings of a meteorological variable, say precip, for a particular day, for a particular basin in each of those 5 years. So the highest precipitation on that date for the 5 years occurred in 2019. And that's denoted by this PP with a subscript of 1. 1 being it's the top rank. And the lowest occurred in 2015. This one is PP5. It has the lowest rank. Now, the ensemble precipitation values determined by the process I described earlier are ranked, and then they replace the observed values according to their rank. So the first ranked ensemble precip, that will replace the PP1 in the observed time series. EPP3 will replace PP3 in 2018, the 2018 time series, and EPP4 will replace PP4 in 2017, and so on. So essentially, the way that we're maintaining or creating time series that make sense spatially and make sense relative to each other, precip and temperature, is that we're using patterns of precipitation and temperature that have occurred in the past to maintain that temporal and spatial realistic patterns. Okay, this is probably the biggest challenge of this whole presentation for me, is to distill that process into 2 slides. So I'm expecting many questions at the end. Okay, so now we'll talk about the Ensemble post-processor, which incorporates hydrologic uncertainty into the HEFS. This post-processor is actually still being developed by the Office of Water Prediction, and it's not yet operational. So I'm going to talk about it today, but know that all the products that we're issuing right now do not include this process. So the goal of the Ensemble post-processor, or ONS post, is to quantify the uncertainties contributed by the hydrologic modeling, increasing the spread in the raw streamflow forecast, and to correct for any biases in the hydrologic models. By combining the forcing and hydrologic uncertainty, the HEFS produces a streamflow forecast that captures both sources of uncertainty. As indicated above, the ONS post models the hydrologic uncertainty independently of any forcing uncertainty. This is achieved by computing the differences between historical simulated flows, or hydrologic model predictions generated with observed forcings, and observed flows. Those observed flows would come from, usually from the U.S. Geological Survey, who maintains the flow records for their gauges across the country. The ONS post uses a linear regression model to capture the relationship between the historical observations and simulations. The regression line can be thought of as an adjustment or adjusted simulation. For each historical date, the difference between the regression line and the observed flow represents the hydrologic error. As with the MEFP, there's a separate tool to estimate the parameters of the regression model, which is known as the ONS post parameter estimator, or ONS post PE. In operational forecasting, each raw streamflow forecast from the HEFS is adjusted by the regression line, thereby removing bias, and a sample of the hydrologic error is added to the adjusted flow to account for the hydrologic uncertainty. In practice, the ONS post error model also uses the observed stream flow immediately prior to the forecast issue time. In this way, the ONS post benefits from hydrologic persistence. So, in summary, this hydrograph shows how HEFS attempts to account for uncertainty in both the forcings and the hydrologic response to those forcings. As with any modeling system, the HEFS has limitations. And I'll talk about a few of them now. It's important to note that the hydrologic bias correction and uncertainty are computed from streamflow data. So they do not account for uncertainties in the flow to stage process. So the Ensemble post-processor accounts for bias and uncertainty in terms of streamflow, and then converts streamflow to stage using a single valued rating curve. That is, for a given flow value, the stage is always represented by a single value. And in our experience, there is often significant uncertainty in rating curves in the north central United States. And this is not conveyed in the HEFS products at this time. During the last 5 to 10 years of experience with the HEFS across the country, there have been many instances when the actual precipitation or temperatures that occur in the forecast period are outside the HEFS ensemble range, leading to streamflow values that are also outside the HEFS ensemble range. So even though we're trying to capture all this uncertainty in the forcings and the hydrology, there are still times when the observed values can end up outside of the uncertainty bounds that we have computed. There are procedural issues that are partially responsible for this, and they are being investigated. However, we need to remember that we are in a non-stationary climate regime right now. And any process that attempts to bias correct meteorological variables based on what has happened in the past is bound to underestimate events in the future, especially during climate change. Our reservoir models also may not accurately represent what actually will occur under any given scenario. Our models are generally pretty robust and are built to handle any scenario that might come about, but they're not perfect. When we're forecasting in real time, creating the time series that we post in HEFS, we're able to coordinate with dam operators and incorporate their feedback into our product or our forecast. This is not something that we're able to do with our partners right now in our service area. I'm sorry, we're not able to do this on an ensemble basis with our partners right now. They don't have the modeling in place where they can come up with these different ensemble hydrographs given our inputs. There are other RFCs who do this, however. Northeast RFC works with the city of New York in kind of a situation where Northeast RFC sends them an ensemble of inflow time series, and then the city of New York will send them back an ensemble of what they would do. Generally speaking, our partners are not able to turn their outflow scenarios back to us that quickly, where they could do it for an entire ensemble. The HEFS products are based on raw hydrologic simulations. The only forecast or input to the process are past adjustments to the simulations that manifest themselves in the initial conditions for the model runs. So all the value added by the forecaster in the forecast period of the HEFS hydrographs is not present in the HEFS products. And finally, I'll just reiterate that the Ensemble post-processor is not operational at this time. OWP is making a big push to get the current version of the HEFS operational across the country, and then they will focus their attention on improving and implementing the post-processor, which accounts for the hydrologic uncertainty. I want to talk a little bit about verification. The Water Resources Evaluation Service was recently unveiled to the RFCs by the Office of Water Prediction. It runs at the National Water Center, and the RFCs are able to submit kind of verification data and jobs to run on their system and produce various graphics. It was designed to verify forecasts of continuous numerical variables, such as precipitation, temperature, or stream flow at discrete forecast locations. Has a variety of options for verifying subsets of data, such as choosing particular times of the year or verifying with respect to particular thresholds. It's also possible to condition on the values of multiple variables, such as verifying precipitation forecasts when temperatures are below freezing. It comprises most of the well-known verification metrics and a few new metrics that are designed for operational forecasting. And these metrics can be produced in a graphical or numerical format. So this is a very powerful tool, and we hope over time to be able to provide our users access to some of these verification numbers in an easy to ingest format to help them interpret the products. Okay. I'm going to just say here basically how to access the HEFS products on the HEFS pages. When you get to the HEFS page for a particular site, you basically just click the probability information tab above the hydrograph and then go to the short-term probabilistic guidance. It's listed as experimental still on these links. What's shown here is an older version of a graphic. And I'm going to kind of go through a newer version here shortly to give you an idea of how to read them. Okay. Before I talk about some of the potential changes in the graphics for HEFS, I would like to just describe this graphic on the left, which is the current version of the graphic. So it shows, I think, about a 2-day observed window of observations here, and then it goes off for 10 days into the future. We're showing a few different things here. One, we're showing the latest operational forecast for the HEFS time series. Here it's shown in these black dots. We're also showing kind of the range of possibilities with these different colored bands. The first internal band here in blue represents kind of the 25th to 75th percent exceedance levels. And the way the edges of these bands are derived is basically we look at every hydrologic trace or ensemble member that was generated by HEFS for each time step. We rank them and then we assign an exceedance probability to them from that ranking. And then what's shown in these graphics is, well, the solid blue line is the median, and then we show the ranges of the exceedance probabilities. So the blue is the 25 to 75, the green is the 10 to 90, and the it's kind of yellowish color, excuse me, is the 5 to 95. And you can see in this particular product that it includes forcings that go out well into the future. In fact, these hydrographs are based on precipitation and temperature ensembles that span the entire 10-day window. So these products fill kind of a glaring gap in our forecast products over the years, where people are wondering what's going to happen 1 to 2 weeks out into the future. What do I need to be prepared for? I think that Craig may be showing this in some of his slides, but we also supply some other graphics to go along with these hydrographs. We have a accumulated precipitation HEFS graphic. We have the air temperature graphic and a snow water equivalent graphic. So those all show the same kind of ensemble ranges, but for these different time series. And as I think Craig will show, they will kind of give you some background information on why the hydrograph is the way it is. Okay, so I'm going to talk now about some potential changes to the graphics. The Nurture Nature Center has a contract with the National Weather Service to look into the best way to create and display graphics for the greatest understanding. They've been at this for the past couple of years and have a renewed contract to continue for one more year. As a part of this, they had some focus groups around the country, I think 4 of them. They had one forecast group with professionals, like hydrologists and engineers and such, and this graphic is a slide from the first meeting from Owego, New York. They showed them the graphic we have now, seen on the left. After much discussion through the day, they arrived at the graphic on the right, where there's much more info in the legends and a different way to depict the probability ranges. They then took that info and had the next focus group meeting with members of the public, emergency managers, and that tier of users. So they started with a graphic that the first group had and had a good deal of discussion. They were given a choice of option A or B, with the main difference being the shading of the probability bands. The shading seemed to have more support, which is the one on the right. Another focus group out in Eureka, California, started with graphics that were slightly different than what was used out east. This seemed to work for their users. But the interesting thing that came out of those focus group meetings was that they have some informational descriptions right there on the graphic. They wanted a mouse over feature with the little eye icons to display info on what they were looking at. So after all the focus group meetings around the country, this is what was finally settled on as the new recommendation for the national HEFS graphic product. The legends and titles have much more info. There's an option to quickly move up and downstream with the arrow buttons in the upper right. They have the mouse over information icons. Excuse me. And there was a definite want and need for some kind of forecaster note, which is seen here in the red band. The users overall were very confident in NWS ability to provide forecasts, but they pretty universally wanted some kind of note directly from the forecaster to express other info, such as confidence. Now, obviously, this might not be easily done when there's widespread flooding going on. Plus, there are typically automated forecasts, so not sure how we might even try to accomplish this. But this is what the forecast groups came up with. One thing I'd like to kind of point out here that is, I think, a really nice feature is this graphic on the right. It's basically showing the probability of exceedance for different, where you can see the probability of exceeding the major, minor, and moderate values during the entire window. And I think that provides a quick, nice summary for people of what they can expect in the next 10 days. So what is feasible? The image on the right is the Nurture Nature Center proposed national product. The group of Eastern Region RFCs did what they could within the confines of our current graphing software. And the image on the left is an example of what we can move to. It doesn't account for everything, but it does incorporate some of the recommendations. To fully get to the proposed graphic on the right, we will need a whole new application for graphic production. So I just wanted to show you this so you know that things are being worked on behind the scenes to make these graphics and products more and more useful. I just want to give you an update as to the status of implementation at the North Central RFC. We are actually generating these graphics for virtually all of our forecast points for WFO internal use only on our internet page. And we've been doing this since early last summer. So we're putting them here on our internet site. We don't want them all going to the public because they all haven't been validated yet. But we wanted to give the WFOs a chance to start working with them and seeing them, especially during the summer when there's lots of opportunities for rain events. We also have some background information, HEFS information on our VLab page. I just noticed that this URL is wrong. It still has the NCEP in the middle of the URL for VLab. So that should be vlab.noaa.gov. So that has a lot of background information on HEFS, should you be looking for it. So during the coming months and during the past several months, we welcome feedback from the WFOs and from your users for that matter. If you introduce these products to your users, we really want to hear what they have to say so we can continue to improve it. WFOs can start training staff and developing outreach materials for their customers. So even if we haven't rolled out HEFS in your area yet, you can still start developing training materials and working with other HPMs to develop training materials. OWP and the NCRFC are evaluating HEFS hindcasting results to determine which locations to publish on AHAPS. Right now, we've made public the HEFS products in the Great Lakes basins. So it's the state of Michigan, eastern Wisconsin, the North Shore of the Great Lake Superior. We're issuing the HEFS products on AHAPS. There's also a few basins in the Mississippi River Basin and the Hudson Bay Basin that we're issuing for as well. But that's only about a quarter to a third of all of our forecast points. The rest of the forecast groups were in the process of evaluating with OWP to make sure that the results are reasonable before we start publishing those. I think right now we're looking at the Des Moines River, the Rock River, the Wisconsin rivers, and some of the other Wisconsin tribes to the Mississippi. those are kind of on deck and they're being evaluated. And we hope to have those ready for the spring. The overall timeline that OWP has is to get them all evaluated and on the web by the end of this fiscal year. So we're working hard to get that done. I also wanted to mention that right now there's a team of OWP and RFC personnel who are charting the next step for the HEFS program. And I'm part of that team. We're going to be working through the rest of this month and the month of February to come up with some next steps. So if you have any feedback from what you've seen so far in the HEFS products, areas that you think need more development, if you think we need different kinds of products for our users, whatever, please let me know and I can incorporate that into our discussions. All right, so in summary, it's obvious that ensemble forecasts are the future. Separating out these different sources of hydrologic uncertainty and using all available observed data to minimize them should improve the streamflow forecast quality in the future. But there's still a lot of work to be done to improve the results. And we ask for your assistance and patience in helping us evaluate the results in the coming months and years. The goal is to improve forecasts for all of our users. So that's all I had. This is my question slide, but I think we're going to wait and let Craig present his information first, and then we'll take some questions.
Yeah, that sounds great, Brian. Thanks for that excellent overview. I learned a ton listening to you go through that material. So I'm going to change presenter over to Craig, and then we'll circle back around for questions after Craig's done. Craig, so you should have a show my screen.
Got it.
All right, looks good.
All right. Well, thanks, Brian and Randy. I really appreciate it, and I hope everybody can hear me over the sound of the wind pummeling the northwest window here of my house. It's a little bit brisk out today, as a lot of us are experiencing. So I just wanted to do a quick evaluation of an event. We had a pretty good convective event in late August, and I just originally put this together as something for our staff to start taking a look at HEFS output and see what type of things it might do for us. But after sharing it with the RFC, decided to share it to a larger audience. So here we are. Just want to start with a little bit of the background for last summer. Of course, it was very dry in the upper Midwest. Going into this event, we were in a lot of severe to extreme drought in our HSA. At the bottom left, the soil moistures were in the lowest 5 to 10th percentile during that time, and it had been for much of the summer. River levels, as you can see on the right, this is one example on the Mississippi, but we had been for over 2 years in the average to well above average flows. But starting from the late spring of 2021 through the summer, we just plummeted and dropped like a rock to where most of our rivers were in the lowest 10 to 20 percentile, and a lot of them were much below low water threshold. So going into this event, things were very dry. Soils were dry, river levels were dry, were very low through much of our area. One thing I will point out, and we'll see this later on, is that in the Wisconsin portion of our CWA, we actually were not in a very severe drought, as for one reason or another, we had gotten pretty good precipitation in Wisconsin through the summer, and it was kind of funny. It was right along the state border, a rare instance of meteorological and geopolitical boundaries matching up. So we'll see a difference as we look at some of the examples coming up of how things looked or how things resulted in Minnesota versus Wisconsin. So lo and behold, late August, around the 27th, 28th, we had a forecast of a fairly major rain event for the upper Midwest, and the 7-day QPF for this event was shown from WPC here on the left. As early as day 3, we had a risk of excessive rainfall, an ERO out for the area, and that was maintained pretty much through the event as we got closer. They were consistently showing this potential of over 3 inches for a fairly large area, and this continued as we got closer. This is the next example. This is a QPF from a 3-day QPF coming up. The center moved a little bit farther south, but still covering a fairly large area. The ERO for day 1 had a large part of pretty much our entire CWA and encompassed quite a few CWAs actually for this event. So we were looking forward to a little bit of rain, hopefully not too much though. So lo and behold, here's a depiction of the rainfall, and the heavy rainfall fell. We did end up with quite a few areas of 4 to 6 inches of rain. We had a fairly widespread 2 to 3 inches over much of the area. Some spots did get a little bit less, 1 to 1.5 here in the upper Minnesota. We'll talk about that. Given the convective nature of this, we didn't necessarily saturate all of entire basins, but we did see some pretty good rainfall amounts over this 2-day period. Just one more depiction of the rainfall using CocoRa's. Anything yellow or more was at least 2.5 inches reported. The orange was 3.5 or more, and the red was 4.5 or more. So again, quite a bit of needed rainfall in this area during the time. And we'll take a look at now at some of the HEFS output for a few gauge locations in our area. These are the locations that we're going to look at. We're going to take a look at the Cottonwood Basin here in the southwest part of our area. Look at Lamberton and New Ulm. We will look at one site on the Minnesota that pretty much represented how the Minnesota reacted. That's also at New Ulm. We'll look at the Cannon River, which was one of the areas that had some of the heaviest rainfall south of the Twin Cities Metro. And then we'll look at a couple on the Wisconsin side. So I won't go over this because Brian covered this all. This was just an example that we used to kind of show what the HEFS output looks like. And you know, as we've seen, we have your most likely area in blue, a 10 to 25th percentile area in green, and about an upper 5 to 10 percentile area in yellow. So I am going to look at, excuse me, I am going to take a look at the precipitation output for each site, as well as the HEFS graphics. So we'll take a look at this. Is just one example here. It's a 10-day ensemble of precip, but what it represents is the precip for the local inflow, the local basin, not the entire basin leading up to that gauge, and that's something to keep in mind. So it's not really like a 1-to-1. If we get, you know, in this case, 4 inches of rain, we would expect a forecast up in the yellow on the HEFS graphic. That doesn't work that way because there's a lot of other factors working into it. But just something to keep in mind. This is does give an example of what type of precipitation we might see in the local area based on the HEFS ensemble. And so I'll be showing those precipitation graphics, and then I'll show some of the actual HEFS output as we're leading up to each event. And once again, explaining most likely area in blue, next most likely in green, least likely in yellow, and we could theoretically also go above that, less than 5% probability of that. So first one we're going to take a look at is the Cottonwood River at Lamberton. This is kind of in the upper reaches of the Cottonwood River. They were looking at forecast precipitation, pretty widespread, 1 to 1.5 inches, looking very likely, with some outside probabilities of 2 to 3 inches. As we moved closer to the event, it stayed pretty consistent that our main precipitation for that area should have been was looking at about 1 to 2 inches with some probabilities up to 4. As we look at what the resultant probabilities on the river were, again, we're starting off extremely dry. We're down at about 100 CFS coming in. The median would bring us up over the next couple of days up to a possibility of around 500, and then you can see the other probabilities here as we move forward. couple more, as we got closer to the event, it started to get a little bit better focused on when the main rises might be. And then this was just 48 hours before the main rises. And you can see the median stayed fairly low. We were looking at, you know, around 300, 400, 500 CFS with an outside chance of reaching, you know, 6,000 or something like that. So that could have been quite a major raise. This is not, by the way, a forecast point. This is one of our data points, and this is one of the advantages of some of the output that we're seeing from the RFC is that we now have some guidance to take a look at for some of our non-forecast points, which is really good to see. So now let's take a look at what actually happened. This basin did get a fairly substantial amount of rain. We did see a couple of 3 to 4 inch reports in the upper part of the basin. There were even some 6 inches plus just outside the basin. We did have some flash flooding in that area. But as we see in the actual hydrograph, we did pop up a little bit between the 30th and 31st, about 2 to 3 days after the heaviest rain fell, just right up to the upper part of the most likely scenario. We'll keep looking forward compared to the other graphs. But again, mainly we ended up with river levels in the most likely category through this event. Going downstream at just a single slide on the river down at the where it flows into the Minnesota. Again, it remained within that most likely scenario. There was some potential if we had gotten extremely heavy rain through the whole basin that we could have seen something getting up into flood stage. But I think the extremely dry antecedent conditions that we had led a lot to where we just stayed right pretty close to the median throughout the whole event. Taking a look at the Minnesota River, also at New Ulm, the forecasts again were pretty similar in terms of the amount of rain expected or potential, you know, around an inch, inch and a half, 2 inches, with some outside chance of 2 to 3. And the HEFS forecast based on this event, again, we had a little bit more of a range, looking at the potential river levels, but nothing really substantial, again, because we were so dry going in. Look at the progression as we move forward here, and the result of that ended up staying even below the most likely category for this event, and in fact quite a bit below by the time we got down to the end of it. But again, I think a lot of that had to do with how dry we were coming into this event. So here, by the way, this is where the river gauge is, and if you look, most of the upper Minnesota only got in about the 1 inch category. So all of this was funneling down to our gauge location in this case. We'll take a look at the Cannon River. This is I did this one on a single slide as well. The precip forecast for this area was around the most likely category was in the 2 to 2.5 inch range, and did have some potential for some pretty decent rises with that. As the results of that, we had a couple of rises based on some of the 2 heaviest bands of precipitation that came through. This area did get quite a bit. We did see some 3 and 4 inches in this area, but once again, we stayed within the most likely range through this one. Excuse me. Now we'll take a look over on the Wisconsin side. This is the Chippewa River in Eau Claire. Forecast rainfall, again, pretty much all of our areas have the same, very similar rainfall as we saw on those initial QPFs, and that is a pretty good large area of 1 to 2, maybe 3 inches, with an outside probability of some higher amounts. In this case, the river levels forecast on that, based on this information, where our median or most likely range was now getting up above axiom stage for this point. We'll go with a couple progression here as we got closer to the event, still showing that possibility, and even around a 10% chance of getting up to flood stage with this one. By the evening of the 27th, the top end had come down a little bit, not quite as likely to get up to flood stage, but we still are showing a pretty good indication of getting to at least action stage from our median rainfall and median river levels. What actually happened, we stayed right around the median throughout this whole event. Moving closer, we actually were on the lower end of the median, and what's interesting on this one is as we got to the nearest forecast of the event, we stayed quite a bit below the actual forecast. Now, some of this could be that the Chippewa River does have some dams upstream that may have been doing some that we're changing their flows, and those would not be reflected in the HEFS forecast. And then last but not least, we're going to take a look at the Eau Claire River at Fall Creek. This is a small basin that is just southeast of the city of Eau Claire. Once again, the rainfall was pretty close to, they were all the rainfall forecasts were all very similar. Show a couple more as we got closer. We did have some potential for some high-end rain possibilities of around 6 to 6.5 inches. But again, the median for this, or the most likely scenario, was going to be in the 2 to 3 inch range. So the HEFS forecast based on that, we were so low coming into this, there was barely any water trickling through this river at the time, and it was going to stay pretty low. This was a much earlier forecast. This is about a week out, but showing potential we'll see a little bit of water get into the basin, but it wasn't showing high probabilities of going up toward action or flood stage. But as we got closer, we started seeing those increase, started getting a better handle on it. We do have at least about a 10 to 15% chance of reaching action stage. And as we got even a little bit closer, that remained. And as things started to rise, we were starting to get a better feel for what we're going to see for a rise here at Fall Creek. So here's the most recent, the last one before we'll look at the results. And what fell, it's kind of hard to see on this map, is was a pretty good area, again, of about 1 to 3 inches in this small basin right to southeast of Eau Claire. There's a little more terrain with this one, so the runoff tends to be a little bit faster for this this basin than some of the other ones. And lo and behold, we did have a nice rise on this. We got up close to action stage, but we did go up into the yellow a week out. Once again, as we move closer, we'll just kind of superimpose the actual hydrograph to it. But they did have the strongest reaction of any basin that we had for this event. And we'll stop here, I think, with one more. So again, not bad. That was a pretty good indication. It did come down a little bit faster than the HEFS, but I think that's something that we'll have to watch in the future and figure out how the best ways for using that information. So just a couple of quick conclusions from just this is again a quick view of one event, is that we can get a good initial idea of some potential rises. I'm really looking forward to taking a look at the temperature profiles and snowmelt this spring and seeing how those can be evaluated and utilized as well. And even if we get a low probability, high amount of precipitation, there are many other factors that we have to keep into account as we're looking at the forecasts. We need to know and know you got to look at your terrain, you got to look at your soil moistures, and know kind of where you are before using this information. And then we have to kind of see how things are going to be on the lower end or the descending portion of the hydrograph. So that is the end of my slides. I'll be happy to take questions along with Brian, and hope this has been beneficial.